We're excited to present Puzzlebot, our chess tactics training system. Puzzlebot is all about personalized chess puzzles. It analyzes your own games to figure out what tactical motifs you struggle with, and then gives you practice puzzles to improve those exact weaknesses. We'll walk through the motivation behind this, how it compares to existing work, our approach and model, which uses a ResNet with SE blocks, the results we achieved, and how we can improve. So, our problem, what we're working on. Chess is hard. Chess has an almost infinite decision space. Each move branches into dozens of possible replies. Even an experienced player struggles to identify which patterns to focus on and which mistakes to avoid. Because of its complexity, merely playing games isn't enough. Without targeted feedback, it's hard to pinpoint exactly where you're going wrong. That's why we address this with tactics puzzles to offer a method to improve skill. Tactic puzzles zero in on common motifs such as forks, pins, skewers, and tactical sacrifices, and give you repetitive hands-on practice with those. By drilling specific patterns, you build your pattern recognition and calculation speed, both of which translate directly into better over-the-board play. So, how can players know what skills to improve? Most puzzle apps let you choose themes or difficulty, but they assume that you do not know your own that you know your own weakness. But our project asks, what if the system could analyze your current games, spot your most frequent errors, and then serve you those puzzles tailored to exactly fill those gaps? That personalized loop, going from game analysis to mistake profiling to targeted puzzles, brings efficiency and focus to your training. So now on to existing approaches. The first paper is Deep Neural Networks with Hand-Picked Features. This uses an approach using handcrafted features such as material balance, piece activity, and more, fed into a neural network to predict puzzle difficulty. This showed some success in rating puzzles more accurately than simple ELO formulas. However, it relies too heavily on those predefined features and treats every user the same, meaning it doesn't adapt to an individual's player's weaknesses. The next paper, Predicting Chess Puzzles Difficulty with Transformers, is another work framed for puzzle difficulty prediction as a sequence problem. They encoded the board, the FEN, as a sequence and used a transformer, which they called the Glickformer, to estimate how hard a puzzle is. Transformers can capture long-range interactions like pieces coordinating across the board better than CNNs. This improved difficulty predictions, but again, it outputs a generic difficulty score for the puzzle, not tailored to any specific player. The third paper, Chess Puzzle Generation Using Stockfish and Genetic Algorithms, took a different angle, which was using a genetic algorithm to generate new chess puzzles automatically. This system evolves board positions by simulating chromosomes of piece placements and uses stockfish to evaluate their tactical value. Over many generations, it produces high-quality puzzles, like mate and N problems, with minimal human input. While it's great for creating content, it doesn't have a way to choose puzzles suited to an individual's needs. There's no personalization in what puzzle is served to which player. So, for our approach, we wanted a pipeline that turns your game mistakes into tailored practice. What it does is it takes a PNG input, puts it through a stockfish analysis, which goes on to a motif classification for the errors within your game, into a personalized puzzle output. So starting with the personalized pipeline and feeding your game into PNG analysis, we start with the player's actual games in PNG format, which is a text record of all moves. Instead of asking the user what they want to practice, we use their own games as a source of truth. Every move they've played is a potential learning point. By mining the PNGs, we let the data of their play guide training. Next, we move on to the Stockfish evaluation, which finds blunders and identifies weakness motifs. We run each game through Stockfish, the strongest open source chess engine, to evaluate every move. Stockfish gives us an evaluation score when a player makes a mistake, or in chess is called a blunder. There's a sudden drop in the evaluation. We pinpoint those blunder positions, essentially having Stockfish flag where the player went wrong and how severely. Then we examine those positions to see what kind of mistake it was. For example, did the player miss a fork, or did they overlook a pin? We label each blunder with a motif category, which is the weakness they need to work on, and this helps isolate the exact tactical pattern that the player struggled with in that moment. Next, we move on to the ResNet classifier, which is classifying the motif and then delivering a personalized puzzle. Once we have a blunder position and suspect a motif, we feed the chessboard state into our ResNet-based motif classifier, which we'll go into more later on. The classifier confirms which tactical motif the position represents by analyzing the board like an image. If it determines, say, this position is a fork motif, the system will then pull a relevant puzzle of that type. In practice, we have a large puzzle database tagged by motif and difficulty. The system selects a puzzle that matches the motif the player missed, and having the appropriate difficulty for the rating. We then present the player with a personalized puzzle addressing that specific weakness. In short, if you blundered by missing a knight fork in your game, Puzzlebot will soon give you a training puzzle that features a knight fork, helping you practice and hopefully avoid missing that mistake next time. This closes the loop. Game analysis leads directly to targeted training, so no need for guesswork or manual selection.
So to discuss our model, we used the Lichess puzzle dataset to train our classifier. We tapped into their monthly public puzzle dumps, which are over 3 million human-created tactics with FENs, solution moves, ratings, and raw theme tags. We extracted each puzzle's board state, or the FEN, the key UCI move, its ELO style rating, and the original theme tags. We collapsed those into 11 streamlined motif labels, like a fork, pin, skewer, or etc., to give the network clear, fixed targets. We adopted a small ResNet block sequence over our 24-channel input. The shortcuts help the network learn deeper spatial filters without vanishing gradients, which is crucial for capturing subtle tactical patterns over an 8x8 grid. The skip connections let us train a deeper model effectively, which is crucial to capture subtle spatial configurations on the chessboard, like a knight's L-shaped fork pattern. We went a step further by integrating squeeze and excitation blocks into each residual block. An SE block is an attention mechanism for CNNs. It squeezes a convolutional block's output by global averaging, summarizing each feature map's importance, then uses two small, fully connected layers to excite or reweight those feature maps channel-wise via a sigmoid gating. Because some motifs are much rarer than others, we chose focal loss to downweight easy, abundant examples and focus training on the hard or underrepresented cases. That helped the model learn to distinguish edge case tactics that standard cross entropy would overlook. As for our performance evaluation, we measure how often our model's top prediction matches the ground truth motif label on held out data. Validation guides hyperparameter tuning, while the test set gives an unbiased estimate of real-world performance once all training is complete. Train and validation sets are created via stratified sampling on the motif labels. Each of our 11 motifs occur at very different frequencies. Forks and pins are common, while skewers and interference are more rare. Stratification ensures that every split has the same class distribution, so we're not unfairly biasing our model to over or underrepresenting any motif in validation. After training, our model achieved accuracy of 47.5%. With 11 classes, random guessing is around 9%. Hitting nearly 50% shows that we're capturing real technical patterns far above chance. The validation accuracy was similar, slightly under the test accuracy, indicating that we did not overfit very heavily. This result validates that our ResNet plus SE classifier is capturing real technical signals from the board, not just memorizing the training set. There's certainly room to improve beyond around 47%, but this is a strong baseline for such a multi-class tactical classification problem. Each correct classification means the system correctly identified a player's mistake motif and can give a relevant puzzle. Even when it's wrong, it's often predicting a motif that's closely related. Our ResNet captures spatial patterns, but transformers can attend globally across all 64 squares and model piece interactions in parallel. Early work like Chessformer shows that they excel at tactical pattern recognition, so swapping in a lightweight transformer encoder could boost motif classification accuracy, especially on complex, long-range tactics. We currently train on 11 broad classes with around 110,000 examples. To cover edge case motifs like mate in 3 or en passant tricks, we can pull additional monthly Lichess dumps and add new subclasses. More data for rare themes and finer label granularity will help the model learn subtler distinctions without collapsing them into noisy other bucket. Our train or validation gap indicates overfitting. Beyond dropout, techniques like drop block or fine-tuning weight decay will force the network to learn more robust generalizable filters. But the real power of a puzzle bot is its continual adaptation. By fine-tuning our model on each user's newly solved puzzles with a small learning rate, we keep their personalized motif detector up to date. This online learning system ensures that the system evolves with the player, addressing fresh weaknesses as they appear. This concludes our presentation. Caden will now take over a live demonstration and explanation of our code.
Hey guys, it's Caden here with the live demo of our puzzle bot. And so you can see as soon as you start up the main.py file, you are provided with an option to provide a PGN file or PGN text. And we're going to paste our text in directly. So from your game, there should be some share option where you're able to copy over all those moves, paste them in here, and then also enter your ELO. For this test, we're going to put in 500s to give us some simpler puzzles to make a better demonstration of, as opposed to difficult ones that I probably can't solve. So right now our PGN is being parsed by our parser function, and after that it'll be stored in a folder accessible by the learning model. And while we wait, it should take around 20 to 30 seconds for us. As you can see here, it classified a certain number of errors and resulted in all of the puzzles that fit the motifs that we have classified. So you can see here we have puzzle 2, and the original position from the game is given here in its FEN. This is something you could take, and it's a board position and what the actual situation, the live situation was from your play. The move you played, the best move that you could have played, and the motif that it falls under. So you can see this carries on for each puzzle. It's classified, and it saves the 10 best drills for you. So now it's giving us the option to see these puzzles in our GUI. Essentially, do we want to play these or not? If you type in no, the program just ends, but we're going to go yes. And it then pops up these boards. So here you can see the theme is deflection. We are playing as white. And so it's likely here, when a move is properly made, it moves on to the next sequence. However, when it is not taken care of, it'll say wrong move. So there's a solve. For example, this next one's a fork, but the wrong move will be this move, right? So it says wrong move, expected this, and you can press R to retry and reset the puzzle, or space to just continue to move on to the next one. And this carries out for around 10 or so puzzles before it quits and you've completed your session. You can upload your next game. So that about completes it for the live demo. Thanks for tuning in.